All right, Chapter 7, we talked about sampling distribution. So here's the first part of Chapter 7. Basically, the big idea here is that when we do statistical inference, so when we did our confidence intervals hypothesis test, we were taking data from a sample and going back to the population. We started by defining what a parameter is in a statistic. The parameter is just a number that describes a characteristic of a population. Usually we don't know that. So when we use mu or sigma, any of those population symbols, the statistic is the number that describes some characteristic of a sample, which we use from the sample data, and we use it to estimate the unknown parameter. So we had like x bar or s squared. So statistics come from samples, parameters come from populations. We also, just to hit the proportions here, p was the population proportion, p hat is the population, as a sample proportion. When we're thinking about sampling distributions or sample variability, because each sample is going to be a little bit different, we have to think about what happens when we take many samples. Because each sample is going to give us a different result. If we remember what we did in class is that we had, I passed around a bag of chips. There was red chips and blue chips in there, and you counted how many reds there were, like what your proportion of reds, and then we plotted the sampling distribution. So you found everybody, like you were in pairs, everybody had their own p hat, and we plotted all those values. So the sampling distribution of the statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So we can't really do that in real life. I could never ask you to take all possible samples from that bag of size 20. So instead we either use simulation or we think about the theoretical distribution. So we have three distributions when we go forward. We have a population distribution, which gives us the value of the variable for the individuals in the population. We have the sample distribution, which just shows this. It's similar to the population one, but it's only for the sample. And then we have the sampling distribution, which shows us how that p hat varies or the x bar varies, depending on what you're looking at. So with the chip example that we did in class, we had a population of 100 blue and 100 red. So the parameter was the population proportion of red chips was 50%. We took different samples of size 20, and each sample, so here's my sample distributions. Some of you might have had a little bit more blue than you had red. Some of you might have been 50-50. So each of these samples were a little bit different, and each of these samples produced a different p hat. Now sometimes we got the same p hat, and then we plotted those p hats to create that sampling distribution. So we have those three distributions here. This is the population. This is what's happening with the sampling distribution, and this is what's happening with the sample, and this is what's happening with the sampling distribution. So then what we talked about were biased and unbiased estimators. Something is unbiased if the mean of the sampling distribution is equal to the true value of the parameter being estimated. So here's the sampling distribution for p hat. So we have all the possible p hats from our multiple samples there. If we took the mean of that, all these p hats, we would find the mean is at 0.5. And the actual population proportion was 0.5. So then that makes my estimate unbiased, because the mean of all the p hats is equal to what I was trying to estimate, in this case p. We also talked about that if you had a larger sample, you're likely to have less spread, so you're likely to hit that target, more likely to hit that target because you're not quite as spread out. So the variability of a statistic. So variability is just another word for spread. So it's described by the spread of its sampling distribution. The spread is determined primarily by the size of the random sample. So larger samples give smaller spread. The spread of the sampling distribution does not depend on the size of the population, as long as the population is at least 10 times larger than the sample. So it goes back to that rule that we had before. All right, we also talked about this target in class. So what we are trying to get with our estimates is we want no bias and low variability. So we want the estimates to be hitting the target, so what we're trying to estimate, and we want it to be consistent. We want it to be always close to that target. Sometimes you might have an estimator that has high bias, so it's completely off from your target, but it has low variability. They're very close together. Sometimes you might have something with low bias, so they are kind of hitting that target, or they're surrounding that target, but they're very spread out. There's lots of variability. This one is really bad. It's way off. There's a lot of bias. It's off the mark, and then there's high variability. It's all spread out. So this last one here is the ideal situation that we're looking for. And you can go through and read that if you're interested. Alright, we also talked about shape of the sampling distribution. We're trying to find something that is like bell-shaped. We'll get into that a little bit more in the other sections. So then this section here, we spent more time with just proportions. I'm going to get back to the beginning. Alright, so we spent more time with just the proportions here. So we did an example here with Reese's Pieces in class, if you remember that. Everybody had their own little pea hats. We went online and reproduced it using technology. You should have known, the shape, when I'm talking about all the pea hats, so the sampling distribution of the pea hats, it was approximated by a normal curve, and there was a rule of thumb that we had. The mean of all the pea hats is just equal to p, and the standard deviation, there was a formula for that as well. Remember, when you're finding pea hat, it's the number of successes that you have in your sample divided by the size of your sample. The formulas for the mean of p hat and the standard deviation of p hat are derived from the binomial formulas. So it's all summarized right here. So again, when I'm talking about all those little pea hats, so remember with the Reese's Pieces, you all found a proportion of orange and then we plotted all those pea hats. Or with the chips, we found a proportion of red and we plotted all those pea hats. So the mean of the pea hats is equal to p. The standard deviation of the pea hats is equal to the square root of p times 1 minus p over n, as long as that condition is met. And then the sampling distribution will be approximately normal as long as this condition is met. And again, remember, you have a population, you take all possible samples of a certain size, find all the pea hats, create the distribution. That distribution has a mean of p and a standard deviation of the square root of p times 1 minus p. Alright, so what they're asking here, so here's an example. So they ask a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students, so 35% of all, that's my P, attend college within 15 miles of home. What's the probability that a random sample of 150 students will give a result within 2 percentage points of this value? So within 2 percentage points means I'm going to be a little bit below it, so 0.33, and 0.02 above it, so 0.37. We found the mean, so the mean is just equal to p, which is 0.35. The standard deviation is p times 1 minus p over the sample size, all into the square root. That's my standard deviation. The condition for normality has been met because both are greater than 10. They went through and standardized it. I would have just told you to, at this point, use, you're trying to find the probability that p hat is between those two values, and you would have done normal CDF 0.33, comma 0.37, comma this mean, comma that standard deviation. So remember, you would have written out like this. You would have had that p hat, but all this right here you would have replaced with that normal CDF command. So again, I would have just done so I would have had 0.33, comma 0.37, comma the mean was 0.35, comma the standard deviation 0.0123. And I would have gotten pretty much this it would have been a little bit more accurate because they used the table, so that would have been my answer. Okay, so I would have written out this statement, I would have drawn my picture, always draw your picture, and I would have had normal CDF there. And then I would write a summary statement. Alright, then the last thing we did here is we did the same thing for the sample mean. Alright, with the sample mean, so this is like when we found all the possible x bars, put them all together, created the sampling distribution. So the mean of all the x bars is just equal to mu. The standard deviation of the x bar is equal to sigma over the square root of n, as long as that 10% condition was satisfied. We did have some rules, though, for the shape. These rules are true no matter what the shape is. This, again, that standard deviation might not be accurate if that condition's not met, but those are still the mean of standard deviation. Alright, so again, now we have a population, we're finding some mean, so maybe we're finding their heights. We take all these possible samples of the same size, find all the x bars, and we plot them to get the sampling distribution. The mean of the x bars is mu, the standard deviation of the x bars is sigma over the square root of n. Alright, when we were talking about shape, if you start off with a population that is normally distributed, the sampling distribution of x bar is normally distributed. So this one here, we start off with a population that's normally distributed. This is for one person, so I would have had you do probability x is greater than 66.5. I would have had you draw on a picture, so draw the picture. You would have said normal CDF, so you would have said 66.5, comma, positive infinity, comma, the mean, comma, the standard deviation, and you would have gotten the answer similar to that one. Alright, this one here, it says find the probability that the mean height of an SRS of 10-year women exceeds 66.5 inches. It's different from this one. This one's talking about one person, and we went back to the population. This one I'm talking about a sample, so I need to find that new standard deviation. So they have the mean of the x bars is 64.5, the standard deviation is 0.79. So this is, since the population is normal, the sampling distribution is normal with a mean of this and a standard deviation of that. So now when I find that they're greater than that, and I'm saying here the probability that x bar, I'm not using p hat, I'm not using x, I'm talking about the sample mean is greater than 66.5. I would have had you draw a picture and shade it. You would have used your normal CDF, 66.5, comma, positive infinity, comma, this mean, comma, this standard deviation. And you would have gotten an answer. So that was easy for heights because they already started off with population. Then the central limit theorem tells us that if your population is normal, as long as their sample size is large, and we'll define that in a second, then the sampling distribution will be approximately normal. We looked at some applets here. And the rule of thumb that we kind of came up with here, so if the population is normal, then the sampling distribution of x bar is normal, no matter what the sample size is. If the population is not normal, the central limit theorem tells us the sampling distribution of x bar will be approximately normal as long as n is greater than or equal to 30. That was the rule of thumb that we used. So if here we're talking about the time a technician requires to do maintenance on the air conditioner, it's skewed right. If you're going to service SRS, a simple random sample of 70 air conditioners, and you have 1.1 hours per unit, will this be enough? So the 10% condition is met. So we can find, there's the mean, it's the same mean as the original one. There's the standard deviation, so that standard deviation is correct. So the sampling distribution is approximately normal with a mean of this, the standard deviation of this, and it's approximately normal. The population wasn't normal, but it's approximately normal because the sample is greater than or equal to 30. So we want to find that the mean time, so x bar is greater than 1.1. Again, they convert it back. I would just have you use the normal CDF command to get your answer, and then we could answer it that way. And that was basically it for sample means.